Hello everyone. In today's paper talks, we have our new guest, Mr. Purushottam Pradhan, who is currently working as an integrated PhD student in Inorganic Physical Chemistry, Indian Institute of Science, Bangalore. So Purushottam did his 11th and 12th in IISc Higher Secondary School, then Colonel Odisha. He's basically from Cuttack, Odisha. He did his BSc in Ravanshaw University, Cuttack, Odisha, and he's currently working in a Department of Inorganic and Physical Chemistry in Indian Institute of Science, Bangalore. His research interests are organometallic chemistry, green and sustainable chemistry. So today his presentation topic is rhenium-based Pincer carbine complexes, a new approach to alkyne metathesis catalysis. Thank you, Purushottam. Now over to Purushottam, who will take us through today's paper. Purushottam, you can take it from here. The screen is yours.
Thanks, Masaya, for giving me this opportunity to present a literature on organometallic chemistry.
Yes, your screen is visible.
I'm giving on a brief discussion about rhenium carbine pincer complexes, a new pathway to alkyne metathesis and catalysis. So before going to the metathesis reaction, I am just giving an introduction about what is the metathesis, the general definition of metathesis. So a metathesis reaction is a type of a chemical reaction when the two reactant molecules react with each other. So the basic inorganic metathesis reaction when an acid react with a base like NaOH, it is formed salt like NaCl with the byproduct water. So this is the basic metathesis reaction. So then can we thought about an organic metathesis be possible? So thanks to the science or the chemistry, there are three metathesis reaction are possible. One is alkene metathesis, another is alkene, and then is alkyne metathesis reaction. So in 2003, they are awarded to Nobel. They are awarded Nobel Prize for the development of the metathesis method in organic synthesis. So now we jump to the alkyne metathesis reaction. The first alkyne metathesis reaction was developed by Schrock in 1981. He used the tungsten metal as the uh, as carbene complexes. They react with the alkyne molecule in presence of toluene at 70 degrees Celsius. They did the metathesis reaction at very low temperature also, and also they got very good yield. Although after that, the DG, now the oxidation state of the tungsten is +6, and also it contains D0 electronic configuration. So there are a lot of research are going on the D0 carbon complexes, non-D0 carbon complexes, which show the alkyne metathesis reaction. So, first of all, the Mayer's group introduced tungsten-based low-valent carbine complexes, which contain D2 configuration, which also shows the metathesis activities for alkyne molecules. But unfortunately, the metathesis reaction is very slow. Then after that, the E&D Williams group also introduced some rhenium-based low-valent carbine complexes. Firstly, they tried the alkyne metathesis reaction with monodentate phosphine-based rhenium carbine complexes, and they are able to did the metathesis reaction. After that, they tried the bivalent phosphine-based rhenium carbine complexes. They are also successfully done the alkyne metathesis reactions. But there is a limitation. The metathesis activity in D2 rhenium complexes are very limited. And tungsten-based carbine complexes. So we are to a target. So now we have to find a strategy to improve the metathesis activity of rhenium 5 carbine complexes, and also to study how the ligand will be affected the metathesis reaction. So in this paper, they reported the synthesis and alkyne metathesis activity of rhenium 5 carbine complexes, which bearing the Pincer ligands. So before going to the work, I am just explaining about what is Pincer ligand. So Pincer ligand is a tridentate ligand that bind to a metal center with three So this is an example of a nickel-based Pincer ligand, and this is very stable at room temperature also. After that, our motivation is and how the barrier of cycloaddition and cycloreversion reaction is dependent on the ligands, the both X type or L type. Here X type and L type are just mentioned for the different type of ligands. And also they are trying to synthesize LXL, LLX, and XLS type of rhenium 5 complexes for the alkyne metathesis reaction. So firstly, they are trying to synthesize the PNP type Pincer ligand. Here, this is the reaction scheme. Here they are used the rhenium carbon complexes 1 react with the amine in presence of toluene, and they are able to get the rhenium based complex 2 with 81% of yield. Here the here the carbine moiety is trans to the chloride ligand and also perpendicular to the plane of the Pincer ligand. They are also did the characterization by 13 PNMR, 31 PNMR and X-ray diffraction studies. After that, they are trying to synthesize PNO type Pincer ligand. This is the type 2 ligand, and this is the reaction scheme where they are again they used rhenium carbine complex 1, and they are able to get the product 3 with 49% of yield. Similar with the complex 2, there also the carbine moiety is trans to the chloride ligand and also perpendicular to the plane of Pincer ligand. Then they did also here the 31P NMR and also the X-ray diffraction study. Then they are targeted to synthesize the ONO type Pincer ligand. So they used rhenium carbon complex 1 and just adding a nucleophile. It is just a simple ligand substitution reaction. That they form the product 4 with they finally concluded that this is the not that expected ONO type Pincer ligand. Here you can see that the rhenium complex is bind through only oxygen atom and the iminium nitrogen atom. But the one OH phenyl group is not bind to the rhenium center. After doing the X-ray diffraction study, they see that this OH group shows some interaction to the chloride ligand. If you will see that. After that, they are trying to find out the activity in the metathesis reaction. Here they took this type of alkyne molecule with react with 2 mole percent of rhenium at 150 degrees Celsius. The temperature is pretty high for this metathesis reaction. They are trying. They did this reaction with four catalysts: rhenium carbon complex 1, 2, 3, and also 4. And first of all, when they tried with the catalyst 2, they got only 4.6% of it. When after that they used the catalyst 3, carbon complex 3, they got 16.1% of it. When they tried with the catalyst 4, they got 0% of it. They concluded that at that high temperature, the complex may not be stable. So they got 0% of it. Then they tried with the ligand 1. They got only 11.1% of it. After that, they are thinking that so they added 2 mole percent of cyanine ruthenium chloride, which is known as a phosphine scavenger into the reaction. After adding the ruthenium chloride, they are for the catalyst 2, they got 65.8% of it, which is a pretty good hit. After that, they're trying with the complex 3 in presence of the 2 mole percent of cyanine ruthenium chloride. They got 28.8% of it. But when they use the complex 4 again, they got 0% of it. So then we can conclude that the ligand is not that much stable at the high temperature. Then they did also some computational studies. Now I'm going to discuss about this. And first of all, they observe what they observed from the above experiments. Maybe the phosphine dissociation is the key step for the metathesis activity of the D2 rhenium 5 carbon complexes. And also, the ligands also influencing the barrier of cycloaddition or cycloreversion reaction that are uh, related with the alkyne metathesis reaction. So, before going to the energy calculation, I am just explaining about the possible pathway for alkyne metathesis reaction. Here in this case, they are tried with the rhenium complex 2A. Here, in our original rhenium carbon complexes, here the triphenyl phosphine is act as a ligand. But for the simplification in calculation, they are instead of using phenyl ring, they are using methyl. On the first step, the dissociation of PME3 will happen, and then it formed 5 coordinated rhenium complexes 7. After that, the alkyne molecule going to react with the complex 7 and for complex 8. Then 2 plus 2 cycloaddition reaction happens, and we got our cyclorhenium diene complex 10. Then the cycloreversion process happens, and we got our complex 9. After the removal of alkyne molecule, we again go to our complex 7 dash. They did the calculation and they confirm and they confirms that the 7 dash and the 7 molecules are isomer to each other. And in between the reaction, the 7 dash is automatically isomerized to 7. So there is no formation of the 7 dash. Here, this is the energy profile for the cycloaddition reaction of modern alkyne carbine complexes. So this is the first step is the removal of phosphine ligand, which is formed to complex 7. And the complex 7 is thermodynamically unfavorable by 9.50 kilocal per mole. Then the addition of alkyne molecule is happen and it forms the stable complex 8. Now we measure the energies from taking reference as the complex 8. Then the 2 plus 2 cycloaddition reaction is happen and form the complex 10. And the complex 10 is also thermodynamically unfavorable by 6.31 kilocal per mole. After that, what is happening? Here, the cycloreversion process is going to take going to take place, and then it form also thermodynamically unfavorable complex intermediate 9, and then the dissociation of alkyne moiety. Then we result our complex 7 again. Here we concluded that the complex 9 is thermodynamically unfavorable and then the complex 8. But the complex 8 and 9 are just isomer to each other. In complex 8, the carbene moiety is trans to the chloride ligand. But in the complex 9, the carbene moiety is trans to the nitrogen atom. And both complex 8 and 9 are stable than the complex 10, metallocyclobutadiene intermediate. Then they did the calculation for the PNO type rhenium complexes. Here, this is the same. The first process is dissociation of phosphine ligand and form the rhenium complex 11, 5 coordinate rhenium complex 11, and then it react with the alkyne moiety and form 12, and then 2 plus 2 cycloaddition reaction is happen and form the unstable product 14 by 7 kilocal per mole, and then cycloreversion process is happening, and then this form complex 13. And here the complex 12 and 13 are energetically very same, slightly less than slightly less because uh, and also the both the complex 12 and 13 are more stable than the metallocyclo intermediate 14. So if you see that the overall barrier for the PNO complex are slightly less than the PNP complexes. So after that, they did the study for the dichlororhenium complexes. Here, the dichlororhenium complexes undergo cycloaddition reaction and form the complex 16, which is thermodynamically favorable by 1.21 kilocal per mole. So we can conclude that it is easier for the dichlororhenium complex to undergo alkyne metathesis reaction than the Pincer carbon complexes 2 and 3. And also, the barrier of cycloadditions are related to the alkyne carbon complexes. And also, there is some uh, electronic and sterical properties that also affect the alkyne metathesis reactions. So in conclusion, they develop new D2 rhenium 5 carbon complexes with as three type of carbon complexes: PNP, PNO, and ONOH bidentate ligand derived from skipase. But unfortunately, they saw only two type of pincer complexes, PNP and PNO, show the catalytical activity at 150 degrees Celsius. But with the stick-based complex, they didn't see any the alkyne product as it is inactive under the similar conditions. And also the environment of ligands also influence the metathesis activity through the phosphine dissociation and also the barrier of cycloaddition reaction of alkyne carbine complexes. So thank you.
Nice presentation, Purushottam. Thank you for sharing your insights on such interesting topic. Now, if you enjoyed this session, don't forget to like, share, and subscribe to our channel to more student paper presentations. See you in the next episode of our literature presentation series. Thank you.